Okay. Maybe a sub n by itself is difficult to figure out if it's convergent. Maybe it doesn't lend itself to a test that you have already been exposed to. Well, what it's telling you is if you can prove that the series that you're interested in, a sub n, is absolutely convergent, which just means that you strip all the signs away, you take the absolute value of the terms and find out if that series converges or not. If that series converges, then we say that it's absolutely convergent, and any series that is absolutely convergent is also convergent. Okay, that's all it's saying. It's just another little thing to put in your tool bag. If you're ever doing a math, take the absolute value of the terms and figure out if that thing converges to find out if it's absolutely convergent. If that is not the case, it's sort of a special series, and it's called conditionally convergent. Okay, so sometimes on your test you might be asked to find out if something's conditionally convergent or absolutely convergent or not. You need to know what these definitions are. Absolutely convergent just means take the absolute value, figure out if that guy converges, and if so, then it's called absolute convergence. Conditional is when you converge but not absolutely. Okay, so you might be asked to do that sometimes. Okay, now what we want to do is go ahead and present the ratio and the root tests. Okay, we're going to just put them on the board. I'm not going to prove it to you. Just like many things in calculus, you could go look at pages and pages of proofs to figure out why the terms do the magic that they do. It's probably worth it for you to do that once to try to understand where this stuff's coming from. But my goal is to show you how to use them. Okay, so what we're going to do is we're going to put them up on the board, and we're going to work some problems to show you how to use them. Okay, so the first thing we're going to do is the ratio test. Okay. And you might think the ratio of what? Well, it's going to be the ratio less than 1, then basically the series converges, otherwise it diverges. And if you take the nth root of the terms and you get a limit less than 1, then it converges, otherwise it doesn't converge at all. Okay? So we're going to work some problems now, but basically when you think about the ratio and the root test, you're going to have to get a feeling for yourself of when those things might help. And the only way you can do that is by working problems. So these types of things are usually going to simplify the terms in a way that you can evaluate. So we're going to go ahead and work some problems now. Okay, so the first series is, what if I had series from n is equal to 1, divide the fraction's top and a fraction's bottom by anything I want, as long as I do it to the top and the bottom both. So n divided by n is 1, and dividing the bottom by n, I will have 1 plus 1 over n, and all of this stuff is cubed. Now you see why I did that. Because now this term, you know, as you go to infinity, this term's going to drop away. 1 over infinity is going to give you 0, okay? So what you're going to have is 3, and you're going to have the limit of 1. All you're going to have is 1 over 1 is 1. 1 cubed, you're going to have 1. So you're going to have 2 times n plus 1 plus 1 factorial over, and you're just going to have what you have here on the bottom. 1 over 2n plus 1 factorial. So it looks a little bit better. I mean, it still looks ugly with all these factorials running around, okay? What we're going to do next is we're just going to go ahead and take the bottom, flip it over, and multiply just like you would do for any fraction. So this is the limit as n goes to infinity of 2n plus 1 factorial over, and on the bottom you're going to have 2n plus 3 on the bottom, and it's factorial. Okay, so let's make sure it's clear that both of these are factorial. Now, here is why the ratio test is used a lot when you have factorials. Remember what a factorial is. If it's 5 factorial, it's 5 times 4 times 3 times 2 times 1. If it's 3 factorial, it's 3 times 2 times 1. Okay, so I can write this as follows. It's easier just to show you by doing. Okay, this is going to be the limit as n goes to infinity. The top I'm going to leave alone, 2n plus 1 factorial. Now the bottom, I have 2n plus 3 factorial. Look at this. I can write this as 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. You see, because I have to continue on multiplying down until I get to 1. I don't know how far away that is, but I certainly know that 2n plus 3 factorial is 2n plus 3 plus 2n plus 2, because I subtract 1, plus 2n plus 1, because I subtracted another one. And then from there on, I keep on multiplying down until I get to 0, and I'm certainly not going to write all those terms out. But the reason I'm going to close to 0, and so in the end, what I'm going to have is 5/9 times 1 when I take the limit, okay? And so what I'm going to have is 5/9 That is the limit, okay? And since 5/9 is less than 1, because it's less than 1, if you go over here to the root test, when you do this thing and you find out a limit less than 1, then it's absolutely convergent. So you could say absolutely convergent, which also means it converges. So it does the regular convergence as well.